Thank you so much. So I'm only going to do a couple of things left over from yesterday, but one of them was this example that I kind of started on the board yesterday, and then it's a little bit too much to write in the middle of the lecture, so I thought that I'd write it up here at the beginning. The other thing, when I started writing it yesterday, I confused myself and convinced myself that I had made a mistake in my notes, which I had not. But what we are writing here are the first few basis elements from this canonical basis from Duke and Jenkins for these two spaces of M24 bang and M minus 22 bang, these weakly holomorphic forms. And what I wanted to illustrate with this was this duality argument. Okay, so this duality that similar to what Zwegers showed or considered, well, Zwegers, Kaneko, Asai, and Ninomea considered in the weight zero case, and Duke and Jenkins kind of looked in a more general case, and then especially because it kind of illustrates Borchard's obstruction theorem here. Okay, so the thing here we have, these are nice integer bases for each of these spaces. Okay, they're diagonalized, so we've got sort of this leading term here. Okay, so everything in this 24 space, we've sort of row reduced, so you've got sort of a handle here that goes, any negative exponent you want, and then all the way up to maybe a 2 there, and then everything else, these coefficients start from 3 onward. Okay, so these first two elements here, these are Cuss forms. This next one down here, this is an Eisenstein series, and then we've reduced by Cuss forms. We've subtracted off some multiples to get rid of those coefficients here in the middle. So this is not exactly an Eisenstein series, but it is a holomorphic modular form, and so on. We're in weight 24. I chose this so that our space of Cuss forms would be two-dimensional, but still level 1. So this top form up here, this is delta squared. Okay? And then this one right here, well, you can get by taking delta and multiplying by some other weight 12 modular form, maybe the Eisenstein series, and then reducing, okay, again. But this is sort of what we get here when we do this fairly straightforward process. Okay, on the other side in M minus 22, if we want to construct these, the way that we might do this is we might start with our weight minus 2 forms. Okay, we already know how to construct those by derivatives of polynomials in the J function. And then we'll divide by delta squared. Okay, that's a great way to do this. Delta doesn't have any poles in the upper half plane. It doesn't have any zeros other than at infinity. And so dividing by delta squared is only going to give us, it's going to increase this pole, but it won't add any other poles anywhere else. So these are all weakly holomorphic. Okay? And then again, we do the same process. Okay? We create some basis of forms, and then we row reduce them here. We don't have any form with order minus 2 or larger. Okay? And so we can only reduce up to that point. Okay? So we've got forms here like this q to the minus 5. Then we have this gap where we've reduced, and then our next piece here is a minus 2, and so on. Okay? So that's sort of how you'd construct these. It's a sort of exercise that's not terribly difficult. If you are familiar with Sage, that's a programming package that William Stein put a lot of effort in to be able to handle a lot of modular forms. Okay? This is a fairly straightforward calculation in Sage. There are several other packages that can do this. But doing calculations like this was one of the first exercises, I guess in the weight zero case, but one of the first exercises that I did when I started doing research in modular forms many, many years ago. Okay. The interesting thing here, and the point that about the duality, is when you make these lists of these forms like this, okay, we're arranging everything in these columns, these tables, and then you start looking down a column here. Okay, so this column here, and then we're going to compare over here on this side to these coefficients over here. Okay, so we've got a minus 48 over there that compares to our plus 48 over here. The plus 195660 over here compares to our minus 195660 over here. Okay, this is a coefficient of q to the minus 1. We find that by coming over here, we look at the form that starts with a q to the plus 1, and look across there for those coefficients. Okay, if we move over to the q to the fourth terms, okay, those we can see by starting over here with our form with a q to the -4 handle, and then start reading across those coefficients that way. Okay, and that's what we get out of these. The constant terms here, okay, we start looking down those constant terms. We find those by coming over here to the weight 24 case and look at the form that starts with a 1 and read across there. Okay, and one interesting point about this, if you're looking in a case where there are no Cuss forms, that means those constant terms are exactly the coefficients of the Eisenstein series. Okay, a little bit more generally, that's what happens when you look at a Poincare series. Okay, those constant terms are the coefficients of the Eisenstein series. Okay. Does that make sense? Does that sort of clarify some of those ideas that I put out there yesterday? Okay. To me, this is a very beautiful aspect of this theory of modular forms, weakly holomorphic modular forms. And again, a big part of that is because this is where I started with my study of modular forms. I was looking at these weakly holomorphic modular forms, these grids, okay, where we can see this duality coming up, right? Okay. And once again, the proof of this, in the case that they're weakly holomorphic, there's a simple proof. If we multiply these two forms together, we have to get something of weight 2, and everything in weight 2 is a derivative of a polynomial in the J function, so it has no constant term. Okay? And so the duality that we're seeing here, we've arranged these forms in such a way that when we do that multiplication, it's going to isolate one coefficient from one side and one coefficient on the other side. Okay? And so they have to add up to be 0, so they have to be negatives of each other. Okay. Is that clear there? Okay. So that's this idea of duality. Okay. There was one other idea that I wanted to talk about from yesterday, just for completeness, well, and also because it connects to some things that Nick is going to be working on. And this connects back to our Eisenstein series. Okay. So remember, we started with our invariant Eisenstein series, EZS, okay, and this was equal to the sum of y to the s divided by c tau plus, I'm using tau, not z, c tau plus d to the 2s, okay, and this converges at least for the real part of s bigger than 1, but we have an analytic continuation to everything except s equals 1. Okay. Now, there's also there's a nice completion of this where we decorate this. Sorry, I have to scroll back here in my notes a little bit. There we go. So gamma zeta pi to the minus s. So if we take pi to the minus s, gamma of s, zeta of 2s times this Eisenstein series, okay, I'm going to call this E star tau of s, okay, and this is again well known from the theory of Maass forms, but this particular version has this very nice functional relation where this is equal to tau of 1 minus s. Okay, once we decorate this, notice this looks similar to the sort of decoration, the sort of thing that you might do to, well, a zeta function to be able to get your functional equation. Okay, turns out that Eisenstein series and zeta functions are pretty closely connected. Okay, but this is our functional equation that lets us go from real part bigger than 1 to real part. Well, that'd take us to real part less than 0. And then again, we have a simple pole at s equals 1. Okay. Now, in order to get our Eisenstein series, our harmonic Eisenstein series that we cared about, right, we want to specify s at a particular value, and then we're either going to do the raising operator or the lowering operator. Okay, we'd specify s at either k halves or, well, 1 minus k halves also works. Okay, We'll normalize things differently, but at least if we want to use this definition, we should use k halves for that being positive. Okay, but that doesn't get us, because of this pole here, s equals 1, that doesn't get us E2. It doesn't get us anything of weight 0. Okay, now we can get around the weight 2 case by doing our raising first before specifying, right? So it turns out that some multiple of E2 star is equal to the raising operator of our E of tau s, and then we evaluate at s equals 1. Okay, but I have to do the evaluation after the derivative because this derivative is going to kill the term that has this pole. Okay, so that'll get us E2 star. Now, if we want an Eisenstein series of weight 0, this pole kind of gets in the way of things. But one easy way to look at this, perhaps we'd take sort of a normalized version of this to get rid of this pole. S times 1 minus s E2 star. Okay, this still satisfies the same functional equation. Okay, now this I can evaluate at s equals 1. Oh, sorry, not E2 star, E star of tau s. This whole thing I can evaluate at s equals 1. Okay, and all I'm getting out of that is just the constant function. Okay, that's just saying that we have our simple pole with a residue 1. Yeah. You're looking at, because of the zeta value, to my knowledge, that answer is no. I know why you're saying that. I believe that the standard Eisenstein series has a 0 there that cancels it, but I could be wrong on that. Is that right? Okay. Great. Okay. So this is one way to sort of think about what should our Eisenstein series of weight 0 be. It should be the constant function. That might be one thing to look at. Yeah. Oh, yes. Yes, yes. Thank you. Yeah, and a lot of times, depending on the source that you look at, they'll define this where you are running overall m and n not 0, and that's exactly that piece. That's that factor. Regardless, this E star is pretty standard. That's the one that has the functional equation, right? Now, there's another way to get something of weight 0 if we really wanted something else. It's an Eisenstein series for weight 0. And this is using the Kronecker limit formula. I'm going to just mention this because it connects to some things that Nick is going to talk about. But what we end up getting out of this is, well, if we take the limit as s goes to 1 of, let's take our E star of tau comma s, we're going to subtract off our pole, our 1 over 1 minus s. Okay. The result here is some constant, which I'm not really worried about right now, minus the log of y eta of tau to the 4th. Okay. So this is not at all a trivial result. This is something that's very interesting to work through. But this is the function that kind of pops out of this. Now notice, it's not a difficult calculation, but if you take the derivative of this, you get E2 star, or a multiple of E2 star. Okay. However, this is not a harmonic Eisenstein series. Okay. So the thing that happens here, if I take this Kronecker function, so log of, oh, I guess I've been using v instead of y. Nope. I've been inconsistent, haven't I? What? Yes, I do want v. Yes. Yes. Everything, we're trying to be consistent with the book, using taus, using v's. I just have to be careful with this. But yeah, so if we take our function log v eta of tau to the fourth here, okay, and we act on this with the Laplacian delta 0, what this is going to do is it is going to give us a -1. Okay? It's going to give us a constant. Okay? So this is not harmonic, but we're not far off. Okay? So now recall, Nick gave us sort of an equivalent idea of what it means for something to be a harmonic, is that it's in the kernel of two copies of this Xi operator, right? So holomorphic means that the Xi operator on F is going to equal 0. Harmonic means that Xi composed with Xi of F is going to equal 0. Now this should be, let's say this is K. This should be 2 minus K. Okay. This function here is something that we call sesquiharmonic. Sesquiharmonic. And this is just that 3 copies. I'm just going to be lazy here, and I'm just going to write C cubed, okay, where I weight things appropriately as I do that, but 3 copies of this is equal to 0. Okay? And this is sort of an interesting fact. The Eisenstein series, in many ways, sort of live at the boundary of our harmonic or sesquiharmonic, at least when we're looking at this S equals 1 term. Okay? E2 is not a holomorphic modular form. It's very close to it. There's a very small correction, but it's not a holomorphic modular form. E2 star is harmonic, but just barely. This Eisenstein series here is not harmonic. It's sesquiharmonic, but just barely. But it's sort of this first taste of the sort of broader theory, sesquiharmonic modular forms. Nick will mention a little bit about work in that direction, but that's sort of this larger theory that we're sort of investigating kind of the ground floor of, or maybe the first floor. Okay. Does that make sense? Okay. Just kind of to give a peek into how things open up from this point. Okay. Now that's the last that I wanted to cover from last lecture. Any last questions before I start erasing? Okay. So from here, we're going to start talking about Hecke operators. The basic theory of Hecke operators is relatively straightforward. It's not substantially different from the theory in for ordinary modular forms. Okay, and so if you're familiar with that theory, some of these first steps might be a little bit boring for you, but I want to at least start from the beginning here. So there is definite study on this. You can definitely see kind of how the same way that stepping up from holomorphic or weakly holomorphic to get to harmonic Maass forms, there's sort of that same process to step up to sesquiharmonic and higher. But there's still a lot of room for investigation. There are some examples, and Nick will talk about some other examples of these. Most of them come through some kind of theta lift, or a Poincare series if you start taking derivatives in the S variable. That's one way where you can start to see some of these things. But there hasn't been a whole ton of work in that direction. There's definitely a lot of room for that. One of the reasons I believe there hasn't been a whole lot of work in that direction is we don't have a lot of motivating examples for this. We don't have a whole lot of situations where we can say these coefficients are meaningful in some way or other, right? With our harmonic Maass forms, we're interested in where they come from because they connect to modular forms, and in many cases, things that we're very interested in that case, whether as functions themselves or because their coefficients are related to things when you're looking at the Mach theta functions. Okay, in the sesquiharmonic case, I just don't think that we've got quite as many examples of where there's coefficients or functions that people really care about for their own purposes. Yeah. It's not to say that they're not there, just that we haven't found them yet. Okay, great. So let's move on from there and let's start talking about our Hecke operators. Okay, so several people in this conference have already talked about Hecke operators. The Hecke operators, so let's say, so for each n in the natural numbers, there is an operator Tn. Okay, now I am going to focus on the level 1 case. In a couple of spots, I might talk about how we adapt this to higher level, but we're going to right now really focus on level 1. Not going to worry about interactions with level. So right now, there is an operator Tn for every n in the natural numbers, okay, where if f is modular for SL2Z, then we have, let's see, so with weight k, then we have that f hit with our Hecke operator, and I'm going to write it this way as an operator on the right, is also modular for the same weight. I could actually write this a little bit more directly, I suppose. Regardless of the function, if I take f, I hit it with my Hecke operator, and then I apply my slash operator for some gamma in SL2Z. Okay. Well, this is the same thing as acting by my matrix gamma and then acting by my Hecke operator. Okay. So I have these operators that commute with this matrix action, at least by any integer matrix here. Okay. Let's see. That's not quite true. No. Yes, that's. I'm going to take that down. That's really not. It's the modularity. The modularity works through, but I can't write it that way. I really can't. And this will make more sense as I give you the definition here. Our TNs are going to be the sums of actions over matrices. Okay? And what's going to happen is when we act by something in SL2Z, it's going to permute those matrices. I can't just commute with it directly. There has to be an action. It's got to permute with these matrices. Okay? But our action for Tn is going to be this action. So we're going to take a sum of f. We're going to act on it by matrices, say matrices mu, where these are going to be matrices within cosets. So we're going to start with integer matrices with determinant n. Okay, so mz is going to equal our 2x2, our set of 2x2 integer matrices, A, B, C, D. A, B, C, D integers, and we have determinant is equal to n. Okay, but I can't act by everything, of course. I'm going to mod out on the left by the action of SL2Z. There we go. That's better. Okay, so I'm looking at these cosets. M sub n? Yes, right here. Yes. Okay, so I'm looking at these cosets. Now, I'm still not done with this definition. Okay, this is maybe a good place to start, but for certain reasons, like to keep things, if we act on an integer modular form, we like to keep things with integer coefficients. And so we would like to normalize this by an n to the, let's see, is it k minus 1 or k halves minus 1? we have, yeah, k halves minus 1. Let me grab this. Okay, we're going to normalize this a little bit. We're going to act by these matrices, and we're going to normalize it. Okay. Now this action, this is where I really am going to use the fact that f is modular with SL2Z, so that this is actually well defined here, right? Okay. In order to look at these cosets, I need to know that choosing a different choice of coset isn't going to change my action here. Okay. Now the fact that our end result is modular, well, that's just the fact if I take this set and I act on the right by something in SL2Z, it's just going to permute these matrices, which means it's going to permute our cosets. Okay. Is that clear? Okay. Now this is a nice formal definition. It's not very helpful in understanding what they actually do. Okay, what they actually do to a modular form. So we're going to make a choice of cosets and make it a little bit more obvious how these interact with a Fourier expansion. Okay. Now it turns out that one choice of cosets that we can pick that will be convenient for our purposes is going to be matrices of the form A, B, 0, D, okay, where A times D equal N, and then B is going to range between, well, I just need B mod D, so let's just pick B to be between 0 and then strictly less than D. Okay. This is a complete set of cosets. Okay, for these cosets. Okay. Now the reason why we like this particular choice of cosets, these are upper triangular. Okay, so if I take a matrix, or let's just work with Q, just the function Q. Okay, again, this is e to the 2 pi I tau. Okay, and now let's send tau to, well, its image under this matrix, right? So tau is going to go to a tau plus b over d. Okay, what happens to Q? Well, we're going to get Q to the a over d. Okay, this part right here is this a multiple of tau, but now my b over d part here is going to give us a root of unity, right? So we'll have let's just say an e of b over d. Okay, this is a dth root of unity. Okay, that particular one. Okay, and so this is really nice. If I know my Q expansion of a modular form, okay, I know what this transformation does to Q. Everything here is linear because it's a change of variable and a normalization at most. Okay, and so this tells me exactly what's happening to the entire Q expansion. Oh, we said of coset. Yes, thank you. Coset reps. Yeah, thank you. Okay, so let's take a look at what this actually does fully on a Q expansion. So let's assume f is modular for SL2Z, and f of tau is equal to some summation a of n q to the n. Okay. Now we might make this a holomorphic modular form. It turns out it works perfectly fine for weakly holomorphic modular forms. So I'm going to just say my summation over n, and I'm going to just be, well, I can at least say that this is greater than or greater than minus infinity, however we want to do that. Okay. Now, when I act on F with my Tn Hecke operator, evaluate this at tau, the end result, again, we're still going to have n greater than minus infinity. Okay. Now inside here, we're going to have a sum over, let's go ahead and call this m here. Not to confuse with my n for my Hecke operator. I'm going to end up having a sum over all divisors of m. Okay. Divisors of m comma n. Okay. Get a d to the k minus 1 a of mn over d squared q to the m. So this is a full expression for any one of our Hecke operators. Okay. This looks a little bit simpler if I restrict to a prime. Okay. So if I restrict to a prime, ftp, let's say p prime. Okay. Then in that case, what we end up getting here is again m greater than minus infinity. I'm just going to have two terms, and I'll index them like this. So I'll have my d equals 1 term and my d equals p terms here, times q to the m. Okay. When d equals 1, okay, I'm just going to have here a of p times m. And then when d is equal to p, I'm going to have a p to the k minus 1 times a of, so this is going to be an m times p divided by p squared. Let's just go ahead and simplify that. Get an m over p. Let's see, did I do the wrong normalization? This is the UP, yes. So I did, what's going wrong here? So I want that to go the other direction. Yes, okay. So there's, is that right? No, so I want this to be, I definitely want this to be on this other side here, which means, yes. So I need this to be n over d to the k minus 1. I need these p's to be on this side. There we go. D to the k minus 1 plus that. There we go. Okay. Good. Okay. Now, when we work with negative weight modular forms, I'm going to want to change a normalization. Okay? I'm going to want the different normalization, the normalization that I just had up there. We're going to want that for negative weight modular forms so that we keep things that behave with an integer, so that they take forms with integer coefficients and send them to forms with integer coefficients. Okay, so if k is, so let's say k is greater than or equal to 2, and I want to work in weight 2 minus k, I'm going to define a renormalized Hecke operator. I'll call it T star for the moment, T star of n, okay, which is, again, going to have the same summation. So f hit with T star of n for the weight 2 minus k. It's going to be, again, n to the k minus 1 times my sum of F hit with mu for mu in these same cosets. Okay. Now notice over here, my standard definition, k halves minus 1. I want this also to be k halves minus 1. Okay. I want the same k halves whether I'm looking positive weight or negative weight. So when I'm doing my negative weight, I'm still keeping k halves with this as a positive number, okay, because I want to clear denominators. Okay. And that's the one where if I take my f hit with t star, so we're working 2 minus k, t star of n of tau, the result is going to be the sum over m times this inner sum d divides the GCD of m comma n of d to the k minus 1 a of mn over d squared q to the m. Okay? So in both cases, we're getting integer multiples of each of these coefficients. Okay. Yes? What's that? Oh, this is 2 minus k. Yeah. So I'm working in weight 2 minus k in this situation. Yeah. So k is greater than or equal to 2. Working in weight 2 minus k. So again, I like to keep k positive. So 2 minus k is my negative weight, and then this preserves these integrality properties here. Okay. What's that? Oh, where? So these definitions do not work in half integer weight. Okay. There is a full, beautiful theory of Hecke operators in half integer weight, but they look very different from these ones. Okay. And let me just write something about that really quickly here. So there are generalizations. Okay, so generalizations. One of these generalizations is just like you're asking for is half integer weight. K equals so k in, let's just go ahead and say in 1/2 z. Okay. Now remember, going back to Nick's very first talk, in order to get things that are not even integers, we have to change our definition of the slash operator a little bit, right? Okay. And so it shouldn't be too surprising then that we have to change our definitions of our Hecke operators. These are always going to depend on the kind of multiplier system that we have. Okay, so if we want Hecke operators for odd weight, we can do that, but we have to generalize our definition here, incorporating this multiplier system. It's got to behave nicely with respect to that multiplier system, or else we're just going to get zero forms. Okay. Same things with half integer weight. They're a little bit more complicated in half integer weight. In fact, the index of all of our Hecke operators in half integer weight are always squares. We don't have one for non-square integers. Okay. And half integer weights, only t n squared exist. Okay. So I don't really want to spend a lot of time to talk about the half-integer weight Hecke operators, other than to say that they exist, but I'd be happy to talk with you a little bit more after. But their formulas just get a little bit more complicated. And so I'd rather take a little bit more time to understand the integer weight cases before worrying about that. Good. Any other questions where we are before we? For the half-integer weight Hecke operators? Yeah, so, well, the one that comes right off the tip of my tongue is Ken Ono has this book, Web of Modularity. It's not so it's a good reference, and it will refer you to a lot of things. It doesn't contain a lot of proofs itself, but it does have a pretty simple description of these half-integer weight modular forms. Oh, yeah, Koblitz, and Koblitz would be a better book as far as like actually showing you, like walking you through proofs and whatnot. Yeah, that's a great one there, for sure. Good. Yeah. Yes. Yeah. Yeah. So notice what's happening here is Tn is just always going to be this k over 2 minus 1. But when k is negative, this is dividing by things, right? And so if I'm acting on something with integer coefficients, I'm probably introducing denominators if I use this Tn just as it is, right? And so what's happening over there is I'm multiplying by just a multiple of n, right? But it changes it in such a way so that we get this integral action that's happening here. Good, good. Any other questions there? Okay. Let's look at an example of some things that come up with these Hecke operators. So we've had, I think a couple of different times we've had people talk about Kaneko's JM functions, okay? And these are equal to, so, well, let's say J1 is equal to the ordinary J function minus 744, okay? And in general, Jm is equal to J of tau hit with this Tm star Hecke operator. Okay. If we wanted to write this in terms of the usual operator, it's going to be Tm, but then we have to multiply by m. Okay. Otherwise, this introduces a denominator. Okay. Now let's actually look at this in terms of the Q series. Okay. So J1 here is going to equal q to the minus 1 plus a sum from n equals 1 to infinity of C of, I guess I have been using m for my indices today. Nope, I'm using, got to be inconsistent one direction or the other. Let's go ahead and call these Jn. And then we'll use m for our index here. Cm q to the m. Okay? So we have this. So now what happens when I act on it by this operator? Okay? Well, the first thing that I'm interested in is what is happening here to the pole. Okay? So, anybody see from the formulas what happens? That's the one where it's a little bit weird because usually I'm writing it in terms of these pieces. Okay? It turns out this is going to turn into a q to the minus n. Okay? How do I see that from those formulas? Where's the term that's showing up? So if I have m as negative n, right? I'm looking at, so I'm coming from the coefficient, go ahead and use some colors here. So if I have m is equal to negative n, okay, I want this to come from the coefficient of minus 1, okay? This piece in here needs to be minus 1. Okay, so if n is negative, or m is negative n, and I have this, right? This is coming from the case. Did I have it right? Okay. dk. Yeah, so this is going to come in from d equals n. But that means I had my normalization right the first time. Did I q to the m minus p? That's right. I did. I had my normalization right the first time. Okay. Apologize. That is, I thought so. It was just throwing me off looking at this board right here then. So this is telling me, right, okay, this is the piece, that was the piece that was throwing me. Okay. I apologize for that. I have my normalization off all the way through here. Okay, so that means what I'm looking at here, m is equal to negative n. This piece is supposed to be negative 1, which means, again, d is equal to n. Okay, so this term here is just 1. That's my constant term that's popping out here. Okay, if I'd used the ordinary Hecke operator, yes, this one up here, again, I'm looking at n is equal to minus n. Okay, I still need d to be n. Okay, I would be getting a denominator here, n to the minus 1, and I want to clear that term. Okay, good. Okay, I just need to trust my notes better. Okay, so this is an example that what happens here with this principal part. Okay, and then we see all of these other terms that come through here. Okay, so plus the sum, etc. Okay, but it's the principal part here that I really want to focus on. Now, what happens in the case that we've got a prime? I want to look at some congruences. Okay. So once again, P is some kind of prime. And let's look at JP, which is going to be, again, our original J1 function. And we act on this with the E star Hecke operator. Okay. Yes. What I was explaining. Yeah, so I had my normalization. So when I first wrote this, right, I wrote this with a dk minus 1. And then I got down here, and I thought that I had my p to the k minus 1 on the wrong term. Okay. The reason for that is one of these pieces is kind of contracting things. One of them is kind of expanding them. And when you look at these terms, it's kind of sometimes easy to confuse which one's expanding, which one's contracting. That was the confusion I made here at the board. But I wrote this. I felt that my normalization was off, so I changed it. But I was right the first time. My notes originally were correct. So this is the normalization I need down here for my T star. So the point here, when I have m is equal to minus n, okay, m and n are both this. D has to equal n. This term right here is my minus 1. That's where I have a coefficient that's non-zero. This piece right here now is just 1, 1 to the k minus 1. That's what's going on there. Good. Okay. So now, when I look at JP here, okay, I'm going to end up getting these coefficients, q to the minus p, okay, plus, well, let's see. So I talked about this kind of expanding or contracting the terms. Let's go ahead and separate those and kind of look at this. So on one side, I'm going to have this sum of, so coming from these pieces, okay, we're going to have this sum of C of P times M q to the m. Remember, this is the ordinary Hecke operator, though, so I need to renormalize this, okay? Plus, I have the terms coming from this piece, okay? I sum my p for my renormalization times this p inverse. We're going to cancel c of m over p q to the m, okay? And this is, again, greater than minus infinity, m greater than minus infinity, okay? Now this right here, this is a little obnoxious to look at, okay? These coefficients, well, just by convention, we say that this is going to be 0 whenever this is not an integer, okay? So let me just go ahead and rewrite this. This piece right here is going to become this sum of Cm times q to the m times p, okay? This is the part that's kind of expanded. I'm spreading out my coefficients, okay? And then, of course, I still have those terms over there, p times c of mp q to the m, okay? Now, if I want to look at a congruence mod p, what's the first thing that you notice? This entire series here, those coefficients are all integers, so this entire series vanishes mod p, okay? So that vanishes mod p, so this entire thing is congruent to the sum of Cm q to the m p, okay? The sum where we've taken the coefficients of this j function and we've expanded them outward, okay? Now, if you work with power series at all, it's not too hard to see that this is also congruent to, we just started with our j function. Well, this piece right here, I guess, let me write it this way. This is equal to our j1 of q to the p, okay? If you work with q series at all, it's not hard to see that that is congruent to j1 of q raised to the pth power. And all of this is working mod p. Okay. So here we've got a congruence in some of these modular forms coming from these Hecke operators. Okay. Now another thing, if we wanted to connect it this way, we know that these JPs, these are polynomials in the j function. Okay. This tells us something about the polynomial. Okay. The polynomial, we already know the polynomial needs to be degree p because I've got that order of pole there. Okay. So this tells me that, so if I write jp of tau is equal to, let's say, some polynomial of j1 of tau, okay, well, then I know that this polynomial of x is going to look like x to the p plus p times some other terms. Okay, everything else here. So this polynomial is actually congruent to x to the p as well. Okay, that makes sense? Okay, so these are some of the congruence properties that come from Hecke operators acting on our weakly holomorphic modular forms. Okay. Things get, and this is all very, very good and nice. If we try to extend this to harmonic Maass forms, we run into problems. Okay, we've talked about the fact that harmonic Maass forms generally do not have these nice algebraic coefficients. Okay. There are situations where they have algebraic coefficients, but they're kind of weird edge cases. These correspond to when there are Cuss forms with complex multiplication hanging around. Okay. For the most part, we generally expect harmonic Maass forms, if they're not weakly holomorphic, we generally expect their coefficients to be transcendental. Here? Yeah, so everything here, this is, everything else now is m greater than or equal to, let's see, oh, we don't have any constant terms anyway. That's strictly greater than 0, yeah. No, these Hecke operators work for n and n. Okay, they work. Well, so if n were the cube of a prime, let's look at those at that formula. That's a good thing to look at. So in the case, so you're looking at, let's start with some kind of Q series here, A of n, Q to the m, and let's act on this by TP cubed, something like this. Okay. Now, what's happening here? This is going to equal the sum of. So we'll have the sum over m. We'll have the sum over d dividing the GCD of m and p cubed, right? Of a of m times n divided by d squared. Okay, and then still working in weight 0. You're happy with that? Okay, so then we're going to have this n over d to the k minus 1 here times our q to the m. Yes, n here is p cubed. N is p cubed, yep. When, sorry, m is equal to what? Minus p. And d is equal to e squared. So you can't have d equal to p squared when m is minus p because d divides the GCD of these two, right? So in that particular case, you're only allowed to go up to p. Yeah, okay. Well, that is an interesting thing to look at, okay? Well, the way that we described, so we started with J1 having no constant term. The Hecke operators cannot introduce a constant term, right? When you look at this formula, in order to get m to be a 0, that can only come from these terms being 0 to begin with, right? So a Hecke operator cannot introduce a constant term. Where's my eraser? Okay. Let's see. How much time do I have? 15? Okay, great. So really quickly with this, let's talk about, this does play, your question plays really nicely into this next piece. Let's talk about what happens when we compose Hecke operators, okay? So if I take a Hecke operator, let's say TA, and I compose it with a Hecke operator TB, okay? So these are our multiplication rules, okay? The Hecke operators commute, okay? This is the same thing as TB, TA, okay? That's true whether or not they're co-prime, they commute. However, if I try to bring them together, it gets a little bit more complicated. And I should look at my notes here, or I will make a mistake. But yeah, so this is going to equal the sum of D divides, again, the GCD of A and B, D to the K minus 1, T to the A times B divided by D squared. Okay. Very similar thing if I look at my renormalized ones in negative weight, okay? This is going to equal TB times TA is going to equal the sum B divides AB, okay, of, well, again, I'm going to assume that K is the positive weight number here. It's going to be a D to the K minus 1, T star, AB over D squared, okay? This is positive. This is in weight 2 minus K, okay? So as long as I write it this way, we end up getting these same formulas here, okay, and they line up nicely, okay? Does that make sense? Okay. Now these Hecke operators, okay, the action that we described, especially when we write them in terms of these coset representatives, the coset representatives with these upper triangular matrices, okay, they behave very similarly when we're working with something that maybe has a non-holomorphic component to it, okay? And so these formulas generally go through basically the same, even if I change this C, I guess over here, let's say this, if I gave this an argument with respect to the imaginary part here, V, okay? They basically go through pretty much the same, okay? So my point there is we can extend these to our harmonic Maass forms without any real trouble, okay? They'll behave on the holomorphic part of the harmonic Maass form exactly the same. On the non-holomorphic part, yeah, we're still doing the same thing and just focus on what's happening with the e to the mx component, the part that's I guess the unitary part of the exponential. Okay. So extend to harmonic Maass forms. Maass forms. Okay. And when we do this, it's worthwhile to see what happens when we interact with the differential operators that we've looked at. Okay, so if f is some element of h of 2 minus k, then we have the following results. Oh, let's see. And T is, let's see, Tn is a Hecke operator. Okay, Tn is some Hecke operator. Oh, I want T star, okay, and to be some Hecke operator here. Then if I apply the Xi operator, the F acted by, so wait, 2 minus k Tn, okay, this goes through very nicely, and we end up getting the Xi operator acting on F, and then we get the corresponding weight k Hecke operator up here. Okay, this is another motivation for the renormalization that we looked at here. Okay, and the reason for this, remember when we wrote these Tn's, we wrote them as this sum over the action of these matrices that are then normalized in a certain way. Okay, the action of the matrices carry through the differential operator just exactly as they are. So we want to have the same normalization on the right and the left. Okay, and so this goes through very nicely just like that. Okay. Second one is the dk minus 1. Okay. dk minus 1 of f of 2 minus k Tn star. Okay. This is now going to equal this one is going to change. This is going to turn into an n to the k. Oh, no. That's right. I'm looking at my Poincare. This one is actually still going to go through exactly the same. There it is. K minus 1 of f acted on by the positive weight corresponding Hecke operator. Okay. So those go through just exactly as they go. What's that? Oh, yes. Yes. subscripts on the C, superscripts on the D. There we go. Okay, good. So those just carry through exactly like that. Okay. Where are we at? Just a couple minutes here. Okay. With this, it's very easy to consider or move this to look at the Poincare series that Nick talked about yesterday. And this is, again, specifically for the integer weight SL2Z Poincare series. Okay, but the Poincare series, as Nick just defined them in those cases, all behave very nicely with respect to these operators. Okay, so we end up having here that, okay, so let's see, so in weight K, so we're looking at the positive weight forms, okay, we have that, get this right here, Pk comma m hit with the Tn Hecke operator is equal to the sum of n over d. D divides, again, the GCD of m and n to the a minus 1, p of k comma mn divided by d squared. Okay, I have a Hecke operator, I act on it, or a Poincare series, I act on it by a Hecke operator, I can write the result cleanly in terms of these Poincare series. Okay, if m is 1, this simplifies a lot because there's only one choice of d here that divides the GCD. Okay, and so we end up getting the dkm dk1 hit with Tn, okay, is equal to, in this case, n to the k minus 1 dk n. Okay. In the negative weight side, the Harmonic Maass form Poincare series, we get a very similar result. On weight 2 minus k, we get that if we start with our Poincare series here, 2 minus k comma m, I act on it with my Tn Hecke operator, again, weight 2 minus k. My result is the sum dk minus 1 f 2 minus k comma mn over d squared, and again, the same d divides the GCD of mn. Okay. Yes, thank you. We go with that. And of course, if I simplify to the case m equals 1, I act on that with my Hecke operator, 2 minus k. In that case, d is just 1, and I end up getting just my Poincare series, 2 minus k comma n. Okay, good. Okay, any questions with this at this point? Okay. Now you can see, so this probably this case over here in the weight 2 minus k case, the proof of this is pretty straightforward. It's just using the principal parts. Consider the principal part. Okay, the order of the pole. Remember, we said that a harmonic Maass form, negative weight, is uniquely determined by its principal part. Okay, so we see what the Hecke operator does to this principal part. That tells us how to write this as a linear combination of those ones. Okay. In order to prove this one, I'm sure there are several more direct ways to do this, but you can prove it from this result using the interaction between these that Nick wrote using the C operator and the dk minus 1 operator. Okay. And then how the Hecke operators carry through those operators. Okay, open it up for any other questions, but otherwise, that's all I'll do for today.
Okay, thanks a lot, Michael. So we'll break for tea and reconvene at 11:15.